Okay, let's continue. And that's the formula I wrote last hour. And let's calculate what is the A plus delta A. Okay, and we like to calculate S of we like to calculate the difference between these two, and the sum of the terms we can erase. That's this one, they are the same. And then we need to multiply of these two. Okay, if we multiply this term by this term, we can get these two. And the first one can be erased by this one. Okay, then I will multiply these three together. The first one, if I multiply this term, totally I can get 4 terms. That's the first one. And the first one, which is the same as this one, it also can be erased. Okay, then the second one, that's the second one. And the third one, okay, that's the third one. Also remember, in the last hour, this term, which is a 1 by 1 matrix, this one is another 1 by 1 matrix, and you can prove the transpose of this one, which is exactly same as this. So I can erase either one and write a double on another term. Okay, the fourth one, which is the So that's the difference between these two. But right now I erased all three terms of the s, and that for some terms erased. So right now I got only three terms. This one, this one, this one, totally equal to only four terms. And this one is the same as this one. Okay, same. 1 by 1 matrix. And the C matrix is equal to D the inverse transpose, then C equal to D. Then C equal to D. So these terms, actually they are same. So right now I will erase this one and write a 2 in terms of this one. And the last one, remember the delta A, all elements in the delta A vector, they are arbitrary and very small variations of the original values. Okay, so all elements in the delta A vector, they are very, very small values. For other terms, we multiply only one delta A. So for this term, there's only one delta A. This term, there's only one delta A. Only the last term, we got the square of the delta A. So compared to the other two terms, the last term, which is all elements in the last term, they are relatively much smaller than the other two. So right now I'm going to write this one terms close to 0. So we can neglect of this one. So the final one will be the 2 times and this one is equal to 0. This one is equal to 0. Also, I can take out the delta A. Equal to 0. And the 2, we can neglect the 2. Okay, remember the delta A, it is an arbitrary variations. Since you cannot expect, we can control the delta A to make this term always equal to 0. So the only possibility we can always get the 0, which is the inside the parentheses, which is equal to a 0 vector. Okay, so that's the only way we can always get the results always equal to 0. So that's the if the A can give you the capital S, which is the smallest capital S values, then the matrix in the parentheses should be equal to a vector. This vector must be equal to 0. Okay, so you can print the screen right now, and I'm going to erase it. So the variations of the capital S, which means the inside the parentheses, it must be equal to zeros. So you can get the B transpose B times A minus B times small f, which is equal to 0. The 0 vector means the all elements in this vector, they are all equal to zeros. Okay, so I can move the second term to the right. So you will get okay, so that's the final equations. If you like to get the coefficients A, it includes the A0, A1, A2 until the AM. All the coefficients A, which defines the g of x functions, all the coefficients which all the A0, A1 coefficients, the set of the A coefficient, which can give the capital S the minimum values, it should fulfill these equations. And it is a set of the simultaneous equations. So we can use the Gaussian elimination method to solve all the coefficients A. And if you multiply these two together, you will find the B transpose B, which is the if we multiply the B transpose B, then you will get the coefficient matrix for this set of the simultaneous equations. And if we multiply the B by the F, it will be the I think this one should be the B transpose F. Okay, this one should be the B transpose F, I believe. Okay, this one should. You need to correct your note. I forgot the transpose. So the B transpose F will be the that's the B transpose F. Okay, so you will find the final results will be same as the previous results we obtained by we take partial derivatives of all the coefficients A0, A1 until the AM. If we take all the partial derivatives and as them all equal to zeros, then you will get the same result. Okay. So now it's time for you to print the screen. Okay, that's all the previous derivations. That's for the regular regression analysis or the regular least square analysis. And the next method I'm going to introduce, which is called the moving least square method. Okay, let's check what is the moving least square method. And right now, let's say we have the okay, let's say we have the functions. If we got the functions x and f of x, and we have several data. So we have the x1, f1, x2, f2. Totally we got n data. Totally we got n data points. Okay, so totally we got n data points. Okay. In the previous derivation, we got only one. For the regular least square methods, we try to find only one g of x functions. We find only we just find a unique g of x function, and these g of x functions can be applied for all x. So no matter after we find the g of x functions. And these g of x functions will be used to estimate the function values, no matter which x we are considering. And it means for this g of x function, which is used to be estimate the function values for for the entire range of the x. Okay, so later I will try to introduce another method, which is called the moving least square method. For the moving least square method, for the moving least square method, the g of x, which is the the g of x will be different for different center point. So it means if we consider a center point which is different, then we got different g of x function. So actually we have infinity the g of x functions, since there are infinity the points in the considered range. And for all these infinity the points in our considered range, we will get different g of x functions. So you can say the results of the moving least square method, we will use infinited. We will get infinity the g of x function. So for different considered x, we got different g of x. Also, when we consider the regular least square method, the weight of the error, they are always the same. Okay, if we use a weight for different points, then in the for the regular least square method, the wi is always equal to 1. So we will put equal weight for different data points. So that's the E1. That's the E2. So the weight of the air will be same for the first data point, same for the second data point. All the data points, they got the same amount of the weight. The weight of all data points, they are always equal to 1. But for the moving least square method, okay, for the moving least square method, we will use the weight functions for all the data points. But right now, the weight, it is functions of the distance between the data points and the center point. The center point, which is the locations we are considering to establish the approximate functions. Okay, it's time for you to print the screen. Okay, so it means right now capital S, which is the summation of Wi times EI squared. Okay, we will multiply the weight for each data point, and the Wi is proportional to the okay, the Wi is functions of the distance between the data point xi and the center point xc, and the center point, which is also the locations Okay, so remember you can say the center point, which is the considered point. We will establish different approximate functions for all points inside the range. So remember the g of x is not only one function. The g of x, which we got the results are in this derivation, we will get infinite g of x functions. So for different center point, we will get a unique g of x functions. Okay, so what is the shape of the functions? We can draw the diagram, which is the xi minus xc. For the distance which is equal to 0, if the data point exactly located at the center point, then we got the maximum w. And the wi is something look like this one. Actually, it should be symmetric about the vertical axis. My drawing is not so good, but actually the weight function should be symmetric about the center. And you can find different mathematical functions which can give you a function like this one. But usually I will introduce a much an easier one. But the easier one will give you the similar results. Okay, so we have the influence radius. Okay, I will call this one, which is called the R, the radius of influence. So if the distance is greater than the radius of influence, the weight will be equal to 0. And inside the radius of influence, you got different Wi value. As long as the data point which is closer to the center point, you will get greater Wi value. But if the distance is farther from the center point, the weight, the magnitude of the weight will be smaller. If the distance is greater than the r, then the weight will be equal to 0. Okay, so what will if we use a weight function like this one, what kind of the difference we will get? Okay, print the screen, then I will continue. Okay, let me illustrate one example. Okay, assume we got 4 data points. That's the xi of the data points. So what happens if we use weight functions? Okay. For example, if we use the linear weight functions, and if the distance between the data point and the center point is equal to 0, the magnitude of the weight will be equal to 1. And if the distance is equal to 3, and this distance is also called the radius of influence. Okay, so inside this circle, the data point will be considered, but outside this radius, the points will not be considered. Okay, so for example, like this one, let's consider a point which is equal to 5. Okay, if we consider the center point of 5, then which point will be considered? Let's say this one is the x1. Okay, then that's the distance between the center point and the data point. The distance is equal to 2. Then we can calculate the weight for this point. The weight of this point. Okay, since it is a linear gradient, which is 1/3, and if the data point, the distance between the data points and the center point, which is equal to 2, then the weight functions will be equal to 1/3. It will be equal to 1/3. And for the point 6, the Wi will be equal to 1 minus 1/3. The weight is equal to 2/3. And for the points, okay, so the distance between the xi equal to 10 and the center point xc equal to 5. The distance between these 2 points, which is equal to 5. The 5 right now is greater than the r. So the Wi will be equal to 0. Will be equal to 0. Okay, so that's the weighting functions. So the weighting functions is related to the distance between the data points and the center point. So we will introduce the weighting function like this one when we analyze the approximate function g of x. Okay, print the screen. Okay, before I continue, I will introduce the Right now, what is the capital S? The capital S is equal to Wi times EI squared. And that's the mathematical formula which defines the capital S function. And if we use the matrix form, then it can be write something like this one. And but remember, we do not have only one set of the A. Actually, the coefficient A, which is a continuous variable, for different center point, we will get different A vector. We will get different A vector. Okay, so that's the error vector, and that's the Wi. What is the matrix A? Okay, so the W matrix, which is a diagonal matrix, and only the diagonal elements, they are non-zeros. And all the off-diagonal elements, they will be all equal to 0. So they will be all equal to zeros. Okay, so that's the W matrix, that's the E vector. And right now, the capital S can be defined like this one. Okay, can be defined like this one. Okay, I think I will take a break right now, and I will continue to in the third hour.